Welcome to the presentation of our Tailored Structures project. It is a design framework that combines a variety of different computational methods for the development of highly efficient and thus more sustainable lightweight rod joint structures. We will start by briefly introducing and discussing the algorithm and the main parts of the framework. Then we are going to present our demonstrators and finally we draw some short conclusions. But before that, we want to introduce our team. The project is from an academic context. We call it a Teach, Design, Make Research project, which means that we take a research topic as teaching subject and develop it together with a student team involving design and physical realization methods. Our tailored structure team was an international one with students and teachers from architecture and design, from the University of Applied Sciences in Wismar and from the School of Art and Design in Kassel. What is our approach? Our starting points are libraries of inhomogeneous parts, like for instance this physical library of roughly 1,000 individual natural straws, or like this stochastic simulation representing a larger stock of 50,000 bamboo rods. From such part libraries we are initiating a design process which gradually evolves towards one of the most efficient specimen to the best solution within the possibilities of our library members. To get there, we are taking the variability of our building material as an advantage, in the sense that we always try to use the weakest and lightest member possible, the one that just fits structurally and geometrically. Our algorithm consists of two main parts: an interactive open topology modeling pipeline, where most of the initial design work happens, and an optimization and fabrication pipeline, including the assignment of the library parts to the design and the automated node generation. The open topology modeling is based on geometrical primitives through which on one hand we can define the structural elements and nodes of our design, and on the other hand we can use such primitives to assign further properties to the structural members. For instance, selections for geometrical constraining, length is of course crucial in our context, specific support conditions and so on. And we can do this interactively while the structure is dynamically relaxed by the Kangaroo engine. In the second part, in the optimization and fabrication pipeline, basically four things happen: structural analysis, cross-section optimization, member assignment and joint generation. The first structural analysis is performed with one single cross-section only, and this cross-section is chosen to represent some average from the library, so an average of the available parts. The result of this first analysis is then the basis and the benchmark for the subsequent optimization of cross-sections. We use Caramba 3D for both, for structure analysis and cross-section optimization. Then our library tinder tries to date the best fitting members from the library with the structural and geometrical requirements delivered by the optimized design. As structural parameter we use the second moment of area, and of course we need to consider the rod length. Our assignment algorithm is custom made and allows for weighting of the incoming criteria. The implementation favors speed a bit over best matches, but as an option, the classic Hungarian method can also be activated to get better results. To connect the final members, we designed three different joint types so far: a quick and primitive version on the left-hand side, a more sophisticated one using Daniel Pike's multi-pipe component. We can nicely see how this joint can adapt to different lengths and diameter situations. And finally, there is the bamboo version, where the multi-pipe version is enhanced by a rationalized serial expansion friction mechanism. This short video summarizes the process. first relaxation and structural analysis, the numbers already show the progress of the assignment process. Cross-section optimization with tension, compression results visualized, then the notes are refined and made ready for printing. We have tested the algorithm at different stages of development with different models, like such preliminary ones with primitive nodes and with a standardized cross-section, like with this straw structure, where we already tested the entire process with individual natural straws and with a variety of such bamboo structure designs. As a conclusion, a few words about the first tests of our approach. For a given load case in two structures, for some percentiles of our library members, we calculated mass and utilization. So what can we expect from the algorithm? After cross-section optimization, we should have an increase in utilization and a decrease in mass. And this is what we can see in this line. And after member assignment, things should become worse again, as not all optimal member cross-sections may exist in the required number or required length in the library, and this behavior happened as well as expected, but still the resulting mass was less than the benchmark calculations. This was our tailored structures approach. Thank you for listening.